Okay, so everything is going well, or do you get any questions? I think basically you can start from any side, right?
Yep.
So you can either from the first one, if I say, suppose I start from A, then if negation P and the Q is 0, that basically means P and the Q is
Is
1, right?
yes.
If P and Q is 1, that
P is
means it must be P is 1 and the Q is 1.
Q is going.
That's basically based on the factor for the end, right? So if a P and a Q is 1, that both P and Q must be 1. Okay. Now in that case, if P is 1, that means negation P is 0. Q is 1, negation Q is 0. And then negation P or negation Q, because both negation P and negation Q are 0. So 0 and the or 0 is also 0,
0.
which is contradicted to the B, right? So it's basically very straightforward. So this is called a proof by contradiction. So please remember that if you try to prove A is B, then you have to if you try to prove using truth table, you can build the table for A, you can build a table for B. But if you try to prove by contradiction, you have to assume, suppose A is true, B is false, then you got contradiction. Suppose A is true, B is false, then you got a contradiction. You have to prove either way. Okay. So that's the example. Now here's another example. I think I'm not going to actually go over this. So you can actually take a look. I'm going to actually, I think I already posted on the Blackboard. Um, that part is still correct. So I need to correct the other part. There's some kind of typo over here. And also, if you try to prove with truth table for this particular actually, prove that the following statements are logically equivalent to using truth table. So negation of P and the negation Q, and the negation P, negation parentheses P or negation Q, and then negation P and Q. So these two statements are equivalent. Okay. So that means, or I can say these are same, Then you can actually build the truth table on the left side, build the truth table on the right side. You can actually prove that it's true. So, or you can, prove by the, you can also prove by contradiction. So either way. So these are the two basic techniques we can use to prove the concept. And so you can actually check the handout to find more information about this topic. And because this is a very interesting topic, because later on we try to build some kind of computer logic. So the math actually logic is basically built upon from our life experience. So you have actually statement, you can build a compound statement, and you can find out what's the value for this compound statement based on the value of single statement. Now this is exactly the same process of building the computer chip. Okay, so this is very interesting. So if you look at the computer chip, the computer chip is actually kind of logic component. Now, a very complicated logic component is actually built from a very simple one. Okay. Now you probably don't believe that in the modern technology, all this integrated circuit, basically, it contains billions of single logic. For example, like you have a truth table like a 1 and the 1 that's 1 1, or 1 that's 1 0, and the 1 that's 0. So it's kind of a logical operation. But if you actually have a very complicated logical expression, that's basically you can build a very complicated logical expression to perform a little bit more complicated operation. So that's basically, so that's why when we actually study this one, the purpose is not just to stay here, just to say, oh, I know math logic, but the purpose that later on we're going to find out, our computer actually technology is actually built upon these millions of these logical components, a component just like this. So it's almost 9:30. Let me actually just give you a start for the second topic. So we're gonna talk. I'm not gonna finish it, but I just start the second one. So you can actually, if you have time, you can start to look at the second module to see how we're gonna actually apply these Boolean logic, which is actually completely math topic, into the logic of the computer components. So let me actually just give you some kind of overview of the second module. So the first slide is just still the same. It's the Edgley Hall and the Edgley Hall. And the second module 2, it's a Boolean algebra. I'm sorry. Now, Boolean algebra is basically built upon these Boolean logic. It's actually the same as Boolean logic. It's just, we try to make it more like a math actually use the math notation in a bigger way. So we can actually completely, use the concept of it. We're not gonna talk about like some kind of a life statement like whether Paris is a city in France or something like this. We completely you know summarize this concept into some kind of algebra called the Boolean algebra, and then we're going to apply this Boolean algebra in the digital electronics. Okay. So the first part you will find out it's the same as the module 1, but we actually start to use slightly different symbol and the notation. Okay. So Boolean algebra is an algebra. For the manipulation of objects that they can take only two values, typically true or false. Now, it's exactly the topic we talk about in module 1, right? Because Boolean algebra basically talk about like two actually simple statement, two simple statement, and we build a compound statement. And now we actually, we basically try to put in this in an abstractor, and then we could just say it's a manipulation of object that can take only two values, typically true or false. Now, honestly, you can say the Boolean algebra can take two values, true and false, but it really doesn't matter whether it's true or false. It could be on and off, black and white, low and high, or circle, square, or square. A circle is one. You just talk about the math dealing with two states. Is it true or false, on or off? You can actually build the equivalence. Say, I mean, true is on, or false is off, right? So it doesn't really matter. Or low is false, true, high is true, or whatever. So you can build that connection. Then you can put the operation on various different things. Now, the reason for this, we try to actually put this in abstraction is because we try to I try to make you forget about how this large Boolean logic comes from. We just try to actually just think about, the computer now. So because computers are built as a collection of switches, okay, that are either on or off. It's kind of actually switch, but it's in typical in our life you can have a switch like a switch for the light. You can turn on, turn off. But the computer switch is not like a physical switch. It's kind of electronic switch. Okay. So the Boolean actual algebra is a very natural way to represent basic digital operation. Okay. So in reality, the digital circuits basically use the voltages, low and high voltages. You know, so and also to simplify this, you know, we actually use a number, a binary number to represent these two states. Instead of a low voltage or high voltage, we can use number 0 or number 1. Number 0 means low voltage, number 1 means high voltage, or number 0 means off, number 1 means on. So either way, so you just actually try to represent two states. Okay, so it's just common to interpret the digital value 0 as false and digital value 1 as true. So now we're going to switch to the Boolean algebra. So we're only dealing with the number 0 and the number 1. Okay. And also, we try to actually, you know, use a different notation for the conjunction, disjunction, and the negation. Okay. So for the conjunction, in the Boolean logic, we use and, or, not, or we use this, and, or, not, right? Now, we are not going to use this. We try to use some kind of a notation typically used in algebra. Okay. Now, so we use plus to represent or. We use asterisk. More, typically you can think about this as multiplication, but it is not multiplication. It is and in the logical operation. And we use tilde to represent not or negation. Okay, so now we use different notation, not different symbol. Okay, for the Boolean algebra. So now suppose we have two objects, x and y. Now in the previous module 1, we just say, oh, x is a statement, y is a statement. Now forget about a statement. We just say two objects. One object has a value 0, and the other object has a value 1. And then we're going to say a asterisk y. That means you can think about this just like a and y. So that means 0 and 0, that's 0, right? 0 and 1, that's 1, 0. 1 and 0, that's 1. 1 and 1, that's 1. That's the same logic as the truth table we talk about for and. So that's and. But we use this asterisk. Now that's all. We use plus. Okay. So that means 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. So now the operation becomes, we call the Boolean, operation. But it's actually the same as the the module 1, but we just use different notation. Now forget about these things. You just use this. Okay. So that's a negation, but we use tilde. So if x is 0, then tilde x is 1. X is 1, tilde x is 0. That's negation, right? Okay. Now, to make it actually a little bit formal, then we need to build the rule of precedence. So in math, in algebra, when we define a couple of operations, now we have to define the precedence for these operations. because if we don't define this, sometimes it's kind of confusion. Okay, so for example, we have three value A, B, C. Now, if I say A plus B times C, now remember this is not arithmetical. This is not addition. This is not multiplication. This is actually the or. This is and, right? Now, so when you actually do this, we treat just like arithmetical, but it's not. The meaning is different. Now, if that's the case, now we can actually figure out. If I want to calculate A plus B times C, now if it is if it is arithmetical, then we know the precedence, right? Because when we have operations like a plus, addition, and the multiplication, now multiplication has a higher precedence higher than the addition. So if we have operation like this, you always calculate the multiplication first and then the addition next, right? Now, if we want to say, no, I don't want to do this. I want to actually do A plus B first and then do the multiplication. In that case, because the precedence says multiplication first, addition next. Now, if you force the addition, perform the addition before the multiplication, you need to use the parentheses, right? Now, if you have a parentheses, then the parentheses has a higher precedence than other operation. So now you have to deal with the plus first, add these two first, and then multiply C. So A plus B times C and A plus B times C, they are not the same, okay? That's for arithmetic. But now we're talking about the Boolean operation. Now, Boolean operation, what do we say? Okay. Now, we also defines the precedence, okay? Okay. So we basically define the precedence, the priority for each of the operation like this, okay? So if you see the negation, the not operator has highest priority, okay? And then the AND operation has a second priority, and the OR operation has the lowest priority. Now, based on this, now how can we interpret this operation? You have OR, you have AND. So AND has higher precedence than OR, right? So that means you're going to evaluate this first, and then evaluate the OR operation. Okay. So it's kind of an accident that if you interpret this as a multiplication and plus, it has the same priority, so same precedence. But just keep that in mind. This is not a multiplication. This is not plus. But the precedence looks like the same as the arithmetic notation. Okay. So if you want to evaluate A plus B first, then we have, this. Now, in this case, that's not the case. If you want to evaluate the first, you have to put the, parenthesis. So for this, the answer is you're going to evaluate this first. If A is 1, B is 0, C is 0, so B times C, 0 times 0, that's 0 times 0, that's 0. And then 0 plus 1, that's 1. Okay, so the final answer is 1. Now, if you want to evaluate this, just do the actually OR operation first. Then you have to put the parenthesis. Okay, so then A plus B, that's 1 plus 0. And then multiply C, which is 0. So A plus 1, that's A, and the A or 1, that's 1, right? And the 1 and the 0, that's 0. So the answer is different, okay? So that's very important. That's a rule of precedence. Okay. So then let's actually finish this one. This is the last slide that we're going to talk about for today. Suppose I have a Boolean function, a Boolean expression, says I have an x plus tilde y and z. What is the value? Now, which one we're going to evaluate first?
Negation.
Negation.
Negation, right? The tilde y going to evaluate first. So if I try to mark with the parenthesis, this one going to evaluate first. Now, what's the next one?
And
Right? Once you finish the tilde y, then we're going to say they evaluate this one first, right? And the last one is plus
Or.
x. So now we try to actually build a truth table for these Boolean function. Then the truth table, because we have 3 variables, x, y, z. So then the truth table should complete all the possible value. So that means you have to say if x is 0, y 0, z is 0, x is 0, y 0, z is 1, x is 0, y is 1, z is 0. So, each variable has 2 values. Now the combination of this, now you're
8.
going to have total of 8 different combination, right?
Yes.
Okay. So now let's randomly pick one to calculate. I hope that you can fill out this table, but let's fill up this table. Okay. Now, so x is 0, y is 1, z is 1. So negation y evaluated first. Negation y is 0, right?
Yes.
Okay. So then negation y times z, 0 times z is 1, also 0, right?
Yes.
And the x is 0 plus negation y, z, that's 0, it's 0, right? So you can actually do the same thing for each of the values of x and y, z. Then you can build the whole table. So the final answer is this, 0. So you can just fill out the rest of this. Okay. Okay, I think that's pretty much all I want to talk about for today. And do you have any questions?
No, sir.
Any issues or anything you want to talk about? Okay. Well, it's close to the 10
Same
o'clock.
time next week.
Yeah. Okay. So if you have any questions, just email me or come to my office hour. So otherwise, I'm going to say good night for today. Please check the Blackboard, for any assignments, any announcement. Okay. Any question? Okay. So I'm going to say good night. So please check the Blackboard, check the handout and the other material. So we're gonna actually start from here next week. Okay.
Thank you very much.
Thank you.
Good evening.
Good evening. Bye. Good night.
Professor Chen,
Yes.
in the assignment, in the second question,